10-3 is about coefficient of determination and the standard error of estimate. So the first thing that we have to sort of go over is understanding, well, what is the difference of each piece. So the first that they give us is they start off with sort of the basics, and they talk about variation. And so the types of variation for regression models is able to be calculated, and specifically there are 3 types, and really there's 2 types, and if you add them together it's everything. So we call when you add up the 2 pieces and you get everything, we call that the total variation. And then we have the explained variation, things we can explain, and then the unexplained, obviously, which we cannot really account for. It's just random. All right, so let's talk about the total. Let's talk about everything really fast. The total variation is the sum of the squares of the vertical distance y. Each point is from the mean, okay, from the average. And this is what we call, again, the total variation. The total variation is made up, again, of 2 parts, the explained and the unexplained. The explained is attributed to a relationship of x and y, and then the second part is really just due to chance. This is our unexplained, because we can't really explain chance. And so the formula that we have right here is our formula that we're going to use for our total variation. But on top of that, if we take our 2 pieces, which we'll look at in a second, and add them up, it should equal our piece. So let's have a visual of this. If I were to draw a graph and I were to have my regression line and I were supposed to have my actual, let's say my actual is right here. All right, this is my actual. This is the variable y. Okay, and then from my regression line, which is the black line, my regression line is going to have my predicted value. Okay, predicted, we said, is going to be y prime. Okay, y prime. And then if I were to take the average is just a number, because it's just an average. It's just one number. It doesn't change at all. So my average would be, we'll say it's somewhere down here, or whatever it is. And this is going to be my average, and this is represented by y bar, okay? So these are all of the annotations that you sort of need to be aware of as we do this, okay? So this is just, again, talking about the variation, and we're just showing you that the total variation is when you consider from the top, the actual, to the average. This is our total variation. If you want to think about it as our total difference, that might help you, the total height between our actual and our average, which is typically below. So let's look at each piece now. So our first piece is our explained variation. This is variation obtained from the relationship, as we said before, of the x and y variables. And this is our formula that we're going to use. So if we were to draw the same picture as we had before, then we would say the explained variation is between y prime, which is the prediction, and the average. Okay, so that would be between the pink and the orange lines, and this would be our explained information, okay? So then the second piece is our unexplained, okay? This is our variation due to chance, and it follows this formula, which is y, the actual, minus our prediction. And so if we were to draw our picture, again, we're copying down this picture, it would be the difference between the purple and the pink. It's our unexplained. And just to summarize a couple of things, you really need to pay attention to your variables in this particular case. Not because I'm going to ask you to compute anything. You're not going to be required to do that. I'm going to show you a proof of what we're saying is true in a second, but you will not have to do this on your own. But just to be aware of, as I'm talking or as I am putting your homework up on the board, if I ask you, or not on the board but forms, if I ask you, about y or y bar or y prime, you need to know what each variable represents. So just to summarize, you have that y is going to be your actual y value, okay? And then the y bar is going to be your average of all of the y values, okay? And then finally, y prime, again, this is your predicted y value, and you get this from the regression line. You get this from the regression line. Okay, so there is a picture on here, and I know that I drew sort of the picture every single time. You don't have to do that if you print these off. You can just have one picture, or even if you do print them off, you really don't have to separate it. I separated it just to make it a little bit easier to look at, and I feel like the picture is a little small, but that's just me. But you can clearly see that the explained and the unexplained variation are here, and then obviously from top to bottom it is our total variation. Okay, so next I'm just going to prove that what we were talking about is true. So here's our example. It says example 10.9. Find the total explained, unexplained variation for number of absences and final grade. So it tells us what our x value and our y value, or independent and dependent variables, are. And again, I'm not going to require you guys to do this, to write it out by hand or to compute it. I will give this piece to you because you already have enough computations going on in your life, right? So the first thing you have to do, if you were to do this, is to figure out the average. And then once you're done with figuring out the average, you are going to label your x and y, all right? You need to use the regression line, so you would have to calculate your regression line to figure out what y prime is, and then you would have to subtract all of these items, okay? And notice how these are not saying total or explained or unexplained, because in order for it to be the total, explained, or unexplained, you would have to square this. So these are just the values, and again, they've already been filled in. And notice how this last column, which is highlighted currently, is called the residual, because and we'll actually define residual in a second, but this is a very useful thing when it comes to regression lines, the residual, specifically the residual plot, which we'll talk about in a second. But if I were to add everything, and I've already done the addition for you, so I'm just going to go ahead and copy it down really fast. Our our explained information is again from here. This is our explained, and this is our unexplained. All right, so I'm just showing you that all these pieces, I'm going to add downward and get all of my answers, hopefully. My total should be 1,690. My explained is going to be 1,506.714. Now, understand that when we were doing this right here, it did round. We had to round eventually, and so we do have some room for error here due to our rounding, but that's okay. As long as you round to 3 decimal places, you should be okay. Finally, our unexplained variation should be 183.298. Okay, so this formula down here at the bottom, right here, all of this right here, is the formula that you had at the beginning of page 1, which was about total variation. Okay, so they're saying that this value right here, it should equal these two values added. That's what they're saying. So all I'm doing is I'm going to prove to you that this is true. So the total variation is 1,690. All right, our explained is 1,506.714, and our unexplained is 183.298. Now, if I were to add these two values up, it's going to give me 1,690.012. So it's not exactly, all right, but it is very, very close, okay? And again, this is due to our rounding in this area, okay? So I just want you guys to be aware of that, and hopefully that will not cause you to misunderstand or anything. But again, this is just a proof. This is just a proof. This is not going to be anything that I would require you to do on your own. I would expect you to know this formula right here, and that's pretty much it. So as I said before, I said the residual plot is really, really important, and because we actually have our residual plot sort of shown to us, we're going to use it in a second, and so the thing we need to do is we need to define it really fast. A residual plot, as we said before, is y minus y prime, or actual, if you want to write, actually I'll put it off to the side, actual minus the predicted. minus the predicted. That's super important. Sometimes this is called a predicted error. And it's when the values are plotted with the x values, but it's called a residual plot. And we'll show you what a residual plot is in a second. It can be used to determine how well the regression line can be used to make predictions, okay? So a residual is the difference, again, between the actual and the predicted, and it can be used to determine how well the regression line can be used to make predictions. Okay, so these are really, really important. Understanding these concepts are really, really important. So what are you looking for with a residual plot? If you can use a residual plot to determine how well a regression line is to make predictions, well then what are you looking for? Well, you are looking for your points, or your scatter plot, if you will, to be evenly distributed about your line. All right, you need and I'll highlight it, if the residuals are more or less evenly distributed around the line. Okay, that is what you're looking for. So let's use our information from before, and I'll go back and add some information in a second, but let's go ahead and do the residual plot that we had before. So I'm not going to show you. I can assume that you can refer back to page 2 to that column that I highlighted. Remember, it should say y minus y prime, and I'm going to go ahead and I'm just going to label, and so this is how you would label it. Your y-axis would go from top to bottom, okay, with 0 being in the middle, obviously. And I just picked 10 because all of my values are less than 10 or greater than negative 10. So that's why I picked that. And then if I look at my x values, because it says we are plotting our residuals, okay, the difference, and our x value. So if I look at my x values, my lowest value is 2, and my highest value is 15. So I'm going to go ahead and I'm just going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so now that I have this, I'm going to go ahead and plot my points. And since they're my actual, I'll make them purple. All right, or actually they're not. We'll make them blue. Okay, so my first one, I have 6. And remember, it's all related to like the number of absences and then your final grade. So if I have 6 absences, there was a difference of 1. Well, 1 is about there, and we'll say this is 5 and this is negative 5. All right, so my point is about there. If I missed 2 days, then it was negative 9, which is about down here. 15 absences would give me a difference of negative 5, so that'd be right around there. 9 absences would give me a difference of 4, so that's just under that 5 there. That was 9. So then 12 absences would give me a difference of negative 1, so that'll be close to that 0 line. 5 absences would give me a difference of positive 5, so that's above. And then 8 absences would give me a positive 4. So I have this picture. I can sort of see the points, and I will say that it is hard to determine. It's hard to determine with small data. Okay, it is hard to determine with small data, but I will tell you what you are looking for. You are looking for, and you should write this somewhere or draw these pictures somewhere, but what you are looking for is if you have a good fit, your regression line fits it well, then your residual plot should have equal, I guess you could say equal points, equal residual plots in the numerator or above and below your line. All right, but if you start to see a shape, so there's a lot of different possibilities. Remember when we had a curved linear line? Okay, so if I were to have a shape, I would say that's a bad fit. Or if I were to have like a line, sort of a line happening in the residual plot. I'm not talking about scatter plots. Scatter plots are different. If you have a line with scatter plots, that's good, because that means that your you're able to have a regression line. There is a significant difference between 0 and rho, remember? But with a residual plot, it's not good. It means that your regression line does not fit your data very well. It sort of fits it at the beginning right here, but then as you go along, your information gets farther and farther away from what is actually happening, and so therefore it is a bad fit. So concerning that previous residual plot, we can say that this plot shows that predictions are random. However, the small sample size also makes the question or the data questionable for making predictions. So we would need we need a lot more points in order to be confident in what we are saying. So the other piece, and you might have seen it in your calculator, is our coefficient of determination. Now the coefficient of determination is just a measure of variation of the dependent variable, which is your y variable. All right, and so this is a ratio between your explained and your total variation. So if you have your explained and your total, which is the whole purpose of why I showed you explained and total. Like, I understand I said that we're not going to really do that and we're not going to compute it, but knowing that your correlation coefficient is a ratio between the explained and total, that can sort of help you understand where I'm coming from. And so we have this formula right here, which is going to be super important. Something to note about it is R. And remember, R is a correlation coefficient. So remember, correlation coefficient, that is determining our strength and direction of data. Okay, is the data related or is it not related? Is it positive or negative, or is it weak or strong? Things like that. So you can take your correlation coefficient and square it, and you don't even have to worry about computing your variation and total variation. So that's one thing. But since we're squaring it, you have to understand any number that we square automatically becomes positive. So you have to know that this is always going to be between 0 and positive 1. 0 and positive 1 inclusive. All right, and some extra notes is that if r squared equals 0 or is close to 0, well then that means we cannot explain all of the variation. All right, but if it was equal to 1, well then that means all the variation can be explained, or you can explain all the variation. So typically your coefficient of determination is going to be expressed with percentage. So if we were to take the correlation coefficient, or excuse me, we actually did our explained and total variation of the previous problem, then we would go ahead and we would take our explained and our total, and we would put them on top of each other, and we would get our 0.891. And what they did was they just merely took the not the correlation coefficient. They merely took they took the correlation coefficient and they plugged it in, and they got negative 0.944 squared. Okay, so if we were to type that in the calculator, that's going to give us 0.891. Turn that into a decimal, or not decimal, but a percentage, and we get 89.1%. And so we would say, therefore, 89.1% of the variation of final grades, because final grades was our dependent variable, that was the outcome, can be explained by the variation of the number of absences. And so your final statement when doing the coefficient of determination, it should be, if you have your x and y variables, which is your dependent and independent, your statement should follow this format where you take your coefficient of determination, turn it into a percentage, and you would say that percentage of the variation of the dependent variable, whatever your dependent variable is. So I'm going to underline it so that you know that that is something that is going to change from problem to problem. All right, so percentage of the variation of the dependent variable can be explained by the variation of the independent of the independent variable. And again, the independent variable is going to change from problem to problem. So that's why I underlined both of these. But this would be your statement every time. The percentage of the variation of the dependent variable can be explained by the variation of the independent variable. So then the coefficient of non-determination is is going to be the difference between 1 and the coefficient of determination. Okay, so this is our difference of the coefficient of determination and 1. And here's the formula for you. And it represents the percentage of the variation in the dependent variable that can't be explained by the variation of the independent variable. So in the previous problem, when we had that 0.891, if we were to find the piece that we could not explain or that was unexplained, we would find the complement of it, which is going to be 0.109, right, or 10.9%, and we would say that 10.9% of the variation in final grades can't be explained. So it's the same format as before, except now we're saying we can't be explained by the variation of the number of absences. So the last little bit, and really it's not super difficult, especially now that you have your calculator, but there is a piece that we do need to calculate, and so before we get to that piece that we need to calculate, we need to understand that our y value, our y prime, is a value, obviously, but it is what we would call a point prediction of the dependent variable for any given x value. The unfortunate problem with a point prediction is that we don't know how accurate it is. It could be really accurate or it could not be very accurate. And so to overcome this disadvantage, we use a prediction or an interval estimate, and we call that point or interval a standard error of estimation, or we'll say estimation. Okay, so here we have our standard error of estimate, and it is going to be represented by S sub EST. So you can think about S being your standard error, and then EST is your estimation. And this is a standard deviation of the observed y values and the predicted y prime values, and they measure how the data points deviate from the regression line, and then they give you this formula. Now, understand a couple of things. The thing at the bottom is our degrees of freedom. The other thing is that we've dealt with something similar to this before. We had our standard deviation, okay? But the thing about the standard deviation is that it looks at the values as they vary from the mean. Okay, whether it be the sample mean or our estimate or our population mean. But with our standard error of estimates, this is no longer about the values varying from the mean, but this is about our values as they vary from the regression line, Okay, so these are the same idea, but one varies from your mean and the other one varies from the regression line. So as I said before, the standard error of estimation, that can be a specific point or it can be an interval, and so that interval is given to you down here. So let's just practice this really fast. So just continuing on with that example that we were given on page 2, we have all of our data that we had before. We are actually having less of our data. We only have our x, y, our predicted, and then the difference, and then we squared it, and then we added, and we found the summation of that. So the top part we've all done before. We did this on page 2, okay? So that's not an issue. But now that we are finding our standard error of estimation, we are going to take some of those columns and we're going to apply them to our formula. So we're going to take our 183.298, and we're going to put that over the degrees of freedom, which is n minus 2. So we have 1, 2, 3, 4, 5, 6, 7 value. 7 minus 2 is 5. And so we'll take a calculator and we'll find out what 183.298 divided by 5 equals. And when we do it, it should give us 6.055, okay? And if you use a calculator, because you can use your calculator, again, you would have to go stat, tests, and then you would go down to letter F. This should give you the same idea again, but you can get a more specific answer. And again, when you're rounding, it should all equal pretty much the same thing anyway. So we found our standard error of estimation. So let's do the same thing again, but now let's find the intervals. So here is the same problem again, and since we're doing the intervals require a little bit more information than normal. Again, you can find pretty much all of these pieces in your calculator. You just have to look for it. But we have our pieces that we need, and I went ahead and I found some other important pieces for you just to make your life a little bit easier. But we need to find the summation of x, the summation of y, xy, so the same pieces that we've had to find in like chapter 9 and beginning of chapter 10. We can use our calculator to find the regression line. So I just want to do this together just to make sure that we understand the steps that require to go into it, and that it hopefully is a review for you. So here's our calculator. We can double check that all of our stats are correct. I literally have entered this in about 3 times now, and after the 3rd time, I still was getting the wrong answer, and so I had to go back. And really, anytime you have issues or you get the wrong answer, it's because you have typed in your values in incorrectly. So please triple, quadruple check that you are plugging in the correct numbers. After you have done that, I just go ahead and do my L1 minus L3, L1 minus L2, list 1 minus list 2, just because I'm used to it and I don't want to lose that habit. It's a good habit to have once we're doing stuff later. And so I'm going to go to statistics, I'm going to go to my tests, and I'm going to scroll down to F. F says linear regression t-test. I'm going to click that. Make sure my L1 is in X, my L2 is in Y. We're still working with row equally or does not equal 0, and so we'll calculate that. And now I have all my pieces. I have my test value, T, I have my P value, I have my degrees of freedom, and I have A and B. Remember, A and B is our linear regression line. So I'm going to go back and plug that in. And if you look at it, S is our standard error. So S equals 6.0546. So we have all of the pieces. And if we scroll down, we have our correlation coefficient and we have our coefficient of determination. So we have a whole lot here that we can use. So first things first, I'm just going to write down my linear regression line. So here we are back at our page. So we're going to copy down our linear regression line, which is going to be that 102.493 minus 3.622x. And then we're going to plug in our value, because at the very beginning it said find the confidence interval at alpha equals 0.05, when x equals 10. Remember, x is supposed to represent our absences. So we're trying to figure out, well, what would our grade, what is the interval of grades that our grade could be if we were to miss class 10 times. So I'm going to plug in 10, and I'm going to figure out what it's going to equal. And after I plug it in, I should get an answer of 66.273. All right, and I'm going to carry over my estimation, my standard error estimation, and when I carry that over, it should be 6.055. And so notice how now I have all these pieces. I'm going to start carrying them down into my interval from my formula. So this would be and I'm going to erase all that because we only really need to do it once, and then we can copy it again and change the sign. So we got that 66.27 right here for plugging in x, and we have our standard estimation next to our square root. So remember, this can be plus or minus, and alpha is 0.05. I'm just going to write that so we don't forget it. All right, so finding our confidence interval. Our confidence interval is that t sub alpha divided by 2. That is from our t table, and remember our degrees of freedom are -2 now, so it would be our degrees of freedom would equal 5, and we should get 2.571, which is right here. Okay, again, our degrees of freedom, we don't really need that. The other piece we need is we need to figure out what is our average of x, okay, because that's a part of our formula. So that is I already did it for you. I'm just showing you that you have to plug it in. All right, and then I'm going to just go through the formula and make sure you know where these numbers are coming from. So we have our n in 3 locations. We have it here, here, and here, okay? Everything else, that 1 plus, that's already there. It's always going to be there. It's never going to change. It's never going to be like a 12 or 2 or 1.5. It's never going to be like that. It's just going to be 1 plus, and then 1 over n. In this case, it's 7. All right, so then the 579, remember, that's our summation of x squared, and the 57 is the summation of x value squared, okay? So that covers everything that we need. The only other piece we need is our x value, which is from our problem. That's 10. We type all of this into the calculator, and we should get 49.414. All right, since we're talking about grades, that would be like 49%. We would retype the whole thing again and get is less than y, which is less than, and we change all of it to get a plus sign, and it would give us 83.132. So you can be 95% confident that the interval of grades possible for somebody who has missed 10 times in class would be between a 49% and an 83%, okay? And so the last little sentence is just reiterating that one more time. So that is how you go through these problems. The last thing I want to go over is I just want to reiterate that the only thing you guys have to calculate on your homework is your regression, or not your regression, excuse me, your r squared, which is your coefficient of determination. You also have to know how to get to your coefficient of non-determination. And then finally, I just need you to be able to find your standard error of estimation. So please make sure that you know how to do those 3 things. They're very simple. And that is what I'll be testing over or quizzing over on the homework.